You know, what if I told you that there's just one single elegant rule that explains how a planet stays in orbit, how a race car screams down the track, and even how you can throw a football? Well, today, we're going to unlock that very rule, Newton's second law of motion.
That's a great question, right? I mean, you've got a massive rocket blasting off into space, and then you've got a football spiraling through the air. What could they possibly share? Well, as you're about to see, they're both dancing to the exact same tune, a beautiful and simple principle of physics.
I mean, you've totally felt this yourself, right? Why is it that when you kick a ball harder, it goes way faster? And why is it such a pain to get a heavy, full shopping cart moving compared to an empty one? These are all fantastic questions about, well, the very nature of motion.
And here's the crazy part. The answer isn't some ridiculously complex theory that takes years to understand. Nope. It's a single, incredibly powerful, and just beautifully simple idea that Sir Isaac Newton figured out hundreds of years ago. It just cut right through all the confusion.
Okay, so here it is, the big one, F equals ma. It might just look like 3 letters from your old algebra class, but trust me, these 3 little letters hold the key to understanding how pretty much everything moves. So let's break down what each one actually means. First up, we've got F, and that stands for force. And really just think of it as any push or pull on something. It's you pushing a door open, it's the wind hitting a sailboat, it's even gravity pulling an apple down from a tree. Simple as that, a push or a pull.
Okay, next up is M for mass. This is basically just how much stuff is packed into an object. So a big old bowling ball, it has a lot of mass. A tiny ping pong ball, it has very, very little mass. It's the physical substance that a force has to deal with.
And finally, we have A for acceleration. Now, this is a super important one. It's not just about speeding up. It's any change in an object's velocity. So that means speeding up, sure, but it also means slowing down, or even just turning a corner. Any change at all. It's the result you get when a force meets a mass. So let's put it all together. The golden rule. Force equals mass times acceleration. What that really means is that the amount of push or pull you put on something is exactly equal to how much stuff it has multiplied by how quickly its motion changes. And this, right here, is where you really see the beauty of this little equation. It's all about relationships. If you keep the mass the same but you add more force, you push harder, you're going to get more acceleration. It's going to move faster. But on the other hand, if you use that exact same push on something with way more mass, you'll get way less acceleration. It's this perfect intuitive balance. All right, so that's the theory. But honestly, the best way to really get this is to see it in the real world, because it is happening literally everywhere, all the time. Let's make this thing real. So let's do a little thought experiment. Imagine you're standing in front of 2 things, a huge, heavy truck and a lightweight little bicycle. Now you're going to give both of them a shove with the exact same amount of effort. What happens? Yeah, exactly what you were thinking, right? You give that truck a push, and with its enormous mass, it barely even budges. Its acceleration is super low. But you give that same push to the little bicycle with its tiny mass, and whoosh, it takes off. That is F equals ma playing out right in front of your eyes. Okay, you ready for a little pop quiz? Let's put your new knowledge to the test. Let's say you've got an object that has a mass of 5 kilograms, and it's accelerating at a rate of 3 meters per second squared. So, what's the force being applied to it? Come on, you can do this. The answer is 15. If you got that, awesome job. You just multiply the mass, 5 kilos, by the acceleration, 3 meters per second squared, and you get 15. And we measure force in a unit called, you guessed it, the Newton. We write it with a capital N. So the force is 15 newtons. So F equals ma, that's the version you're going to use pretty much all the time. But, to really get the full picture, there are a couple of extra details that Newton himself thought were really important. Here's a cool little tidbit. Newton didn't actually write F equals ma. He thought about it in terms of momentum, which is just an object's mass multiplied by its velocity. His big idea was that a force is what changes an object's momentum. Now, why does that little detail matter? Well, it's absolutely crucial when an object's mass is changing. Think about a rocket that's burning through tons of fuel every single second. It's getting lighter. Okay, and here's another key idea. Think of it like a tug-of-war. If you have forces on an object that are all pulling equally in opposite directions, they cancel each other out. We call those balanced forces. The result? Nothing happens. No acceleration. It's only when one side pulls harder, when you have an unbalanced force, that you actually get a change in motion. That's the real trigger.
Okay, so we've seen it with bikes and trucks, but now let's zoom all the way out, because this little equation doesn't just explain everyday stuff, it literally shapes worlds.
I mean, just look around. Every single car on the road, every plane in the sky, every satellite we've ever launched into orbit, even the robots we built. The design and engineering behind all of it is built on F equals ma. It is the absolute undisputed backbone of all classical mechanics. Our modern world would be completely unrecognizable without it.
Whew, okay, we have covered a lot. So before we wrap up, let's just boil it all down to the absolute essentials. If you're going to remember anything, remember this stuff.
First, the formula you got to know: F equals ma. Force equals mass times acceleration. Second, things only accelerate when there's an unbalanced force acting on them. Third, the more stuff something is made of, the more mass it has, the less it's going to accelerate for a given push. And finally, remember that the direction you push is the direction it accelerates. They're always linked.
And that quote, man, that really just says it all, doesn't it? This isn't just some dusty old equation from a textbook. It's a deep truth about how reality works. A simple push or a pull is what changes motion. And all those changes in motion happening every second, from the tiniest particles to the biggest galaxies, well, that's what shapes the entire universe we live in. Thanks so much for diving in with me.